Hello, good afternoon. Can you hear me? Okay. So it's time to finish with this course. It's time to wrap up, and that's what we are going to do today. First of all, I'm going to show you some slides. The goal of this first presentation is just to summarize the many things that we cover in the course, and also encourage you to keep being interested in computer architecture and maybe even doing research with us. That's what we are going to do in this first maybe 20, 30 minutes. After that, we are going to have a discussion session, which essentially consists in us being here in the DocuCam, solving questions that are we have selected from the optional homeworks and are like very typical homework questions and exam questions. Why is it important to have this kind of session even though you already have the solutions in the website? It's important because you will see how we reason when we solve one of these questions, and this can also help you to understand these questions better and the way that you have to proceed when you are solving these kind of questions in the exam. And in the very last part of the lecture, what we will do is talking about the exam. I'm pretty sure that you will have some questions. We also want to give you some advice, and and hopefully you will be ready for the exam sometime in August. Okay? So let's start with this lecture. 26 is the epilogue. So here, as I said, what we are going to do is wrapping up, talking a little bit about what are the main things that we cover in the course and what should be the main takeaways after having completed this course. Of course, we don't have required readings for this part, but there are some suggested readings for sure, some recommended readings. So recall, what are the major high-level goals of this course? Professor Mutlu already showed you this slide, and this is something that you also have in the website. This course is about digital design, digital circuits, and computer architecture. It's a very complete course. I'm pretty sure that you cannot find easily something with this, with this large span of concepts and this depth that Professor Mutlu employs to cover all the concepts. It's a very unique course in which the main goals are these three. Understanding what are the basics of the way that computers are built, understand what are the principles of design, and understand what are the precedents. And this understanding is important because thanks to that, you have been able to learn how a modern computer works, and real computers work exactly the way that we have explained here. Very important thing, having able to evaluate trade-offs in the design and the ideas. That's why whenever we have explained a new paradigm, a processing paradigm, for example, or architecture paradigm, we have shown pros and cons because we need to evaluate trade-offs, and we want you to think critically about these designs and about these ideas. One thing that you also did is implementing your own microprocessor. Very simple design, but you ended up doing that using your FPGA board in the labs. And in this process, you also learned about how to debug, systematically debug increasingly complex systems, right? So you learn how to debug the designs that you were doing, and thanks to that, you ended up designing this and implementing this simple microprocessor. So those are the main goals, and hopefully you are also you have also been enabled to develop new novel designs. So the focus of the course is on basics, principles, precedents, and how to use them to create and implement good designs. And why these goals? Because you are studying computer science, right? So if you are a doctor, maybe you will end up being a specialist of the eyes, but still you need to know that there is a heart, right? And there's a brain, and there are many other components inside our body. So even if you are going to end up working in the future in something completely different to computer architecture, you will still be working in the computer science field, right? And all the things that we have covered here and all this knowledge will help you to do many things in a right way and in a nice way in the future. If you do hardware design, you will be able to design better hardware. If you do software design, you will be able to design better software. Why is that? Because now you know how the architecture is built, how the computer is built inside. And for example, you will keep in mind that there is a cache hierarchy, and in this cache, probably the caches have certain size in L1 and certain size in L2 and so on, and you will keep in mind what it's going to be probably stored in the cache when you are running the program that you are coding, that you're writing. So this knowledge is, it's useful in all aspects of computer science. So hopefully also designing better systems, be smart when having to make design decisions and having to analyze trade-offs. Of course, understanding why computers behave the way they do. But the most important things are these three, right? Which actually are like even more general than the course. It's an engineering course. It's a computer science course. So one thing is that you have learned or are learning, not only in this course, also in other courses, but here it's something that Professor Mudlu really had in mind when he designed the course. He wanted you to learn how to solve problems better and also think in parallel. What does it mean? I mean, unfortunately, well, our mind is not so multi-threaded or SIMD as some of the paradigms that we have covered here. But we are able to take many different things into account when we are doing some analysis, when we are analyzing a system or when we are designing a system. There are different things that we are able, and you will have to keep in mind when you're doing that, right? So you will need to think about, the SIMD units if you're writing SIMD code, or how the general, how an out-of-order processor works if you are simply writing some sequential code. But as I said before, you will also have to take into account what might be happening or can be happening with the cache hierarchy and so on. So this is what thinking in parallel means, and also, of course, thinking critically, right? So being able to evaluate designs in a critical way. And this was a long way since the beginning of the course. We started with the transistors as building blocks, and we ended up talking even about system software mechanisms. Maybe not so much as we would have liked, but still we did. And in between, we talk about logic design, ISA, and microarchitecture, which are the main components of or the central components of computer architecture. The key execution paradigms we call pipelining, out-of-order execution, SIMD, multi-threading, etc. And finally, in the last lectures, the memory system, main memory, caches, and virtual memory. So key takeaways, takeaway one, everything that was covered here is real and it's used in real systems. So this is very important. Second thing, all the principles that we cover applied broadly, even though, we talk about GPUs, for example, right? And GPUs are, let's say, specialized accelerators, let's say. In the beginning, they were designed only for graphics processing, right? But they are based on some principles that apply much broadly, right? Because you remember that we also have SIMD units in supercomputers like the Cray one or Cray XP that we have in CAB building, or We also have SIMD instructions in general purpose CPUs as the ones that you have in your laptops, for example. And third takeaway, again, trade-off analysis and critical thinking. And hopefully this is already clear. This is the entire view of, the transformation hierarchy that it's the central part of this course. What we have, the narrow view, what we have in the middle is the hardware-software interface, which essentially is the ISA, and the microarchitecture, but the expanded view or computer architecture is much wider, spanning from the device and the logic to the algorithm and the programming languages. So what's the best way to approach this course? You already know this slide, but it's good to recap, not only to make sure that everything with respect to the course is clear, but also, to give you the right mindset for the final exam. So take it as a learning and grow experience. What we cover here changed the world in some way. It changed computing systems, and I guess you know that computing systems changed the world in the last 20, 30, 50 years. And everything will be more and more important for obvious reasons. And even if you are not a future architect, all the things that we cover here, as I said before, will be important for your future. So focus on main goal here, focusing on the understanding, learning, and critical analysis, because these are the agents of your growth. And the course, Professor Mutlu designed this course with that goal and that focus in mind. Unfortunately, it wasn't possible to cover everything related to computer architecture. Computer architecture has many more topics, which are also very, very interesting. But this is something that you will still have time to worry about, because there are many ideas, creativity, trade-offs, and problems to solve, and things like how to make systems scale, how to improve performance, improve energy consumption, deal with reliability or security issues. These kind of things are really important when designing computing systems these days. And this is something already obvious in some, let's say, recent trends. For example, AI and machine learning. We are designing accelerators for this type of applications, and they are extremely important in all the fields where AI and machine learning are being used. You can, for example, search for Tesla cars, and you will see that they have especially design machine learning accelerators to deal with all the workloads that are needed for self-driving. There are many hardware security issues that we have to worry about, and we have to come up with nice ways to solve them. We have Rowhammer, Spectrum, Meltdown are things that we have covered here in the course. And there are also new execution paradigms like processing in memory, or new technologies like memory technologies, for example, like non-volatile memories, like PCM or ReRAM, and many more that are being studied these days. So there are many things to do. Visionary lecture that you might want to watch again, I guess that most of you already did, is Professor Mutlu's ETH inaugural lecture. Okay. Some takeaways. Recall this from lecture 2. This is an exciting time to be understanding and designing computing platforms. And there are many challenges, many exciting problems to solve. Why is that? Because the world is changing. There is a lot of data out there, and we should be able to use this data in the smartest possible way. This is so it's said that we are in the era of big data, right? So what should we do with all that data? We should be able to use it to make stronger and better computing systems, but also we need to create these systems to be able to analyze all this data. And there are challenges and difficulties to solve, like, for example, energy, reliability, complexity, and so on. This is more or less The state-of-the-art applications are ever more demanding. There are emerging technologies, like, for example, memory technologies that I just mentioned, many requirements, systems, and security, reliability issues, so many things to do in computer architecture. Here you can see a list of some of the ideas and topics that we couldn't cover in this course, but hopefully if you're interested, you will keep learning in later courses that we have. I will talk about them briefly. For example, prefetching or run-ahead execution, emerging memory technologies, SSDs and storage, interconnection networks, and so on, so on, so on, as you can see. And you need to understand all of them very well if you want to build efficient computing systems, right? It's the same as Calatrava had to do when he designed this building in New York. He had to know everything about real architecture before daring to design this thing. And even though he did, you remember also that he had to replan, he had to redesign because there were some security issues. So this is something that you will also have to do when you design systems, software, hardware in your future career. Okay, as an example of one of the things that we couldn't cover, and it's super important in real-world systems, and it's something that you can actually find in every CPU these days, is prefetching. But I think that Professor Mudl already mentioned prefetching in the course, right? But let's very briefly talk about prefetching. The idea in prefetching is fetching the data before it's needed. So you know that we have a memory hierarchy, and in this memory hierarchy, we have a very large memory, which is, let's say, at the bottom is the main memory, typically DRAM, and then we have different levels of cache. Ideally, we will always find the data, the program will always find the data that needs in the L1 cache. Why is that? Because it's the closest one to the core, so it's the fastest, right? So if we are able to make something to put whatever data is going to be needed into this L1, then the performance will be the best possible performance, right? Unfortunately, this is not always possible. And it's not always possible because sometimes we have unpredictable memory accesses. But in many, many programs, it's something that is possible, is doable, because there are predictable memory accesses. For example, if you have a streaming access pattern, which essentially means that you have to go over an entire array element by element. For example, if you're doing one vector addition, you are adding vector A plus vector B element-wise. So if your code is sequential, you will go to element 0, element 1, element 2, and so on. As you already know, if you go and try to access element 0, and this element 0 is not in the cache, you will have to go to main memory, then because you will have a cache miss, and then you bring an entire cache line, which probably will contain 4, 8, or 16 of the elements. So after having missed in the first memory access, then you will have several hits. But right after that, you will again have a miss, so you will need to go to main memory again. If you analyze this program, you see that the access is sequential. So every let's say 8 accesses, you will have a miss, and then 7 hits, and then again a miss. And the miss happens because you need to fetch the next cache line. So if you already know that, you can directly go to memory and prefetch this cache line and put it in the cache, in the L1 cache, for example, so that as soon as the CPU needs to carry out this memory access, the data will be already in the cache. We will have a cache hit and much higher performance, right? It's not always possible, as I said. There are some applications, for example, graph processing, where the accesses are more random, so much more difficult to predict. Well, there are 4 questions around prefetching: what to prefetch, when to prefetch, because if I prefetch something like very much in advance, it might turn out that because it's not being used for some time, it will get replaced, so evicted from the cache. So I also have to write to fetch in the right time, and also put the data that I read in the right place as well. There are different ways of doing this. Hardware prefetchers, there are hardware prefetchers. We will cover this in later courses, but also software prefetching. This is something that you can already find, for example, ISA instructions that are software prefetching in Intel CPUs. And many different questions to answer, or many different, angles or aspects of prefetching that need to be taken into account. And one example, or one, let's say, sort of prefetching is run-ahead execution, which is what Professor Mudlu, one of the things that Professor Mudlu did in his PhD thesis. He had, let's say, a dream when he was starting with his PhD thesis, and his dream was designing the perfect cache, which means that every time that I need to access to memory, instead of having to go to L2, L3, or main memory, I will find the value that I need in L1. So that's the perfect cache, always a hit, So if I have a perfect cache, I will, the CPU will be doing some computation, executing instructions, represented here by this green box, and then we will have a memory access, for example, here, one load, certain value that I need from memory, and because the cache is perfect, I find it in the cache, so it's a hit, and right after that, we continue with the execution, and then another hit in a different memory load, and then some more computation. This is a perfect cache, but unfortunately, it's not what we have in reality. In reality, we might have something like this. We will start computing, and at some point, we need to go to memory because we don't find the data in L1 or L2 or L3, so we have a miss, and we need to go to main memory. And this takes some time to be served. The miss takes quite a bit of time. Maybe in the beginning, we still have some independent instructions, and we can continue executing them in the CPU, in the course, but at some point we will have to stall and wait until this miss is served. When we get the value from memory, then we can continue computing, and we will find another miss in the second load. And again, we have to stall until the miss is served and we finalize the computation. So as you can see here, most of the time of the CPU is not being productive. The CPU is idle because there are no more instructions to execute. And the rest of instructions are dependent on the load instructions here, the load instruction that is missing in the cache here, and here, this load too. With the run-ahead execution, what we can do is doing some kind of speculative execution in which, if we are lucky, hopefully, we can reach to more accesses, miss in the cache, and start serving these misses, these memory accesses, in parallel. So in a way that we can exploit memory-level parallelism. And this way, we will end up saving a lot of cycles. The idea is something like this. We start the computation, and at this point in time, we have a load to memory, so a load from memory. We are missing in the cache, and again, same as before, we have to go to the main memory, right? But now, instead of just simply stalling the pipeline, what we do is entering what is called the run-ahead mode. That essentially means that, first of all, we save the architectural state. Do you remember what's the architectural state? It's the value of the program counter and the contents of the register file. So if we have these two, we can recover the point of execution whenever we want. So what we do here, right before starting the run-ahead mode, is saving the program counter and saving the contents of the register file. And we enter this run-ahead mode. Probably some of the instructions that we will execute during this run-ahead mode, which essentially means that we keep executing instructions of the program on the pipeline, maybe some of these instructions that will be executed will be unproductive in the future. You know why? Because those computations will probably be dependent on these miss that we have here. So probably the result of these computations will be useless, let's say. But the good thing is that we will probably reach this second load. And if we reach this second load, what is going to happen is that we have a miss. But observe that now the miss, we found this miss pretty faster with respect to the regular execution on an out-of-order core. So right at this point in time, we also ask the memory to serve this memory access. So as you can see, both memory accesses happen in parallel for some time in a way that when we find again, so after returning from the first load, we, let's say, recover. You remember that we had a checkpointing, checkpointing. So we go to the checkpoint, we take the value of the values of the register file, the value of the program counter, and we continue with the execution. Now this execution is correct. And the good thing is that during this computation, the second miss is finally being served. So when we go again and try to load this value, this memory access here, which is the same memory access as here, then we hit in the cache and we can continue the execution. We are saving all this stall here, so we end up saving all these cycles. So, was this useful? This research in particular? Yes, it was. And actually, one machine where this run-ahead execution was implemented is this Rock. And here you can see some results on a real system for different cache sizes. You can see the normalized IPC. Scout was the name that Sang gave to this run-ahead execution. For the same size of the L2, you can obtain up to 40% better performance. But also a very interesting thing here is that you can get exactly the same performance by having a much smaller cache. For example, 7 megabytes smaller in the case of a Scout here, or 12 megabytes smaller in this case, if the original cache was 16 megabytes. Okay, this is, as I said, just one example of the many things that we still need to cover in computer architecture. This is the paper, the original paper about the run-ahead execution. This is a shorter one that was published in Micro Topics, and here are some more recommended readings. So, if you want more of this exciting thing that is computer architecture, you have future options, like, for example, taking the Bachelor seminar, taking in the future the computer architecture master's course, read all the papers that were recommended here in the course, and analyze them, discuss them with us if you want. You can reach any of us and send us an email and tell us, I want to discuss this paper with you, or there is something here that I don't understand very well. You're welcome to do that. And of course, you are invited to do research with us if you are interested. This is the beautiful logo of our group, and this is our motto. Think big, aim high, essentially be ambitious, and try to do always the best that you can do. Again, the Bachelor seminar, this one will, we have this seminar every semester, fall and spring semester. The next one, obviously, will be the fall semester. And here what we do is reading papers and analyzing them. In the very beginning of the course, of the seminar, we will offer some papers that we select because we consider that they are very important and useful in computer architecture. Some of the papers are historical, let's say. Some of other papers are very, very recent. And what you do is select your favorite paper, read it, and analyze critically. And after that, having discussion with two of us, two members of the group, which, let's say, act as your mentors. They help you to understand the paper. They help you to prepare a very nice presentation. And someday you go there, and in front of everyone, you give your talk. Why is this useful? Not only because you learn a lot of things about computer architecture from your own paper, from other people's presentations, but also because you will develop your skills for analyzing and synthesizing information, but also your presentation skill, which is something that I'm pretty sure that will be useful for you. You can even watch the video because we record the videos, you know, for grading, for internal use, and if you want to have access to them, they can also be very useful to watch yourself and learn about your own experience. And then we have the computer architecture course where we cover, review many of the things that were already covered here in this course, but we also go far beyond. And if you are interested in doing research with us, which is something super nice, super fun, you, first of all, is email Professor Mutlu and CC me and Mohammed, Lois, and Hassan. Of course, we encourage you to take these 2 courses that I just mentioned and do all the readings and assignments on your own. There are many, many exciting projects here in memory systems, in hardware security, in accelerators like FPGAs, GPUs, heterogeneous systems in general, new execution paradigms, for example, like processing in memory. Several of us are working on that these days, and interaction between security, architecture, reliability, energy, performance, et cetera, et cetera. And also architectures for particular fields, like, for example, genomics and medical and health. Okay, any questions so far? No? Okay, I have 2 quotes for you to think about. The first one is this one: the reasonable man adapts himself to the world. The unreasonable one persists in trying to adapt the world to himself. So therefore, all progress depends on the unreasonable man, which is the one who tries to change the world. This is a quote from George Bernard Shaw. He was an Irish playwright, famous for several of his plays, like, for example, Pygmalion. This is the guy, very serious. And here you have also the second quote also from him, very nice and interesting to think about. Progress is impossible without change, and those who cannot change their minds cannot change anything, right? Sounds good. So keep that in mind, not only for, these exams that are coming now, but also for the next courses that you will take here during your bachelor's degree and for sure in your future career when you are in the job market. This is all for now. For this lecture 26. Now let me switch to the discussion session. Do you have, meantime, any comments or questions?